Question number 1. What is the first law of thermodynamics? First law of thermodynamics. Suppose a system is there. This is a system. If you give dq applied heat on the system, first law of thermodynamics, first law of thermodynamics or thermodynamics. dq equal to du plus pdv. That means pdv or du. dq is the amount of heat you are giving to the system. It will be divided into two equal parts. That is two parts. One is the internal energy, that is equal to it is Cp dt. It is Cv dt. It is R dt. You are getting Cp minus Cv equal to R. Very important formula. Cp is the per mole specific heat at constant pressure. This is Cp is specific heat at constant pressure and Cv is specific heat at constant volume. Clear? Now, this law, first law of thermodynamics, based on conservation of energy. Clear? This is the first law of thermodynamics method in form Cp minus Cv equal to R. Cp is always greater than Cv. If you know, again, Cp by Cv equal to 1 by 2 by n. N equal to 3 monoatomic, n equal to 5 diatomic, n equal to 6 polyatomic. This is gamma. You know this is gamma. Gamma equal to Cp by Cv, 1 plus 2 by n equal to 3, number of atoms present, monoatomic, diatomic, and n equal to 6 polyatomic. This is another formula, Cp by Cv equal to 1 plus 2 by n. Okay. So first question, mathematical equation for first law of thermodynamics. Then I have proved Cp minus Cv equal to R. Again I have told you that gamma equal to Cp by Cv equal to 1 plus 2 by n. That means gamma expressed in terms of degrees of freedom. N is degrees of freedom. N equal to degrees of freedom. Next question I am telling you. Energy per degrees of freedom. Energy per degrees of freedom. Energy per degrees of freedom half kT. K equal to R by N. K equal to R by N. Now, so कि Boltzmann constant internal energy of a gas system, internal energy depends on temperature T. Now, to find out the internal energy of a gas system, first to calculate total degrees of freedom, multiply half kT, you are getting total internal energy of the system. Again, we know two systems, we are going isothermal system, isobaric, next is isoporic, next you are getting isothermal, isobaric, isoporic and adiabatic. In this case, temperature constant, internal is same, isobaric pressure constant, volume constant. In this case, heat exchange between the system to surroundings, no heat will be exchanged. Now in this case we can write isothermal case, already you know PV equal to nRT, gas equation. This is the gas equations. Now in this case you can write Boyle's law, you can write all P1 V1 by T1 equal to constant for isothermal, P1 V1 by constant, but in this case it will be modified. Boyle's law modified PV to the power gamma equal to constant. This is very important. PV to the power gamma equal to constant. P1 V1 by T1 equal to constant for isothermal case, and for adiabatic Boyle's law modified in the form. Now we write adiabatic work done, isothermal work equal to RT log E base V2 by V1. If it is adiabatic work equal to CV T1 minus T2 or R by gamma minus 1 P2 V2 minus P1 V1. P1 V1 equal to P2 V2. Okay, so these are the gas laws we use to solve the problem. Next, I am telling you in PV diagram, V and P. Now V I, V F. What is observed in this case? It is clear. Gas expands. Work is positive. Work is positive. Clear? Volume Vf greater than Vi. area of PV area will give you work done. Area equal PdV equal to work done. Now in this case it is clear that work is positive. That means system does work on surroundings. Remember it. System does work on surroundings. Next, we are dealing with the chapter transmission of heat. Next, we are dealing with transmission of heat. Suppose conduction. For conduction, consider a rod. It is a rod. Thermal conductivity K thermal conductivity. Clear? Area of cross section A. Area of cross section A length is L. Hot temperature at A equal to T1. Cold temperature at B is T2. Now how much heat will flow from A to B? We have heat flow per second equal to Q by T equal to Ka by L T1 minus T2. It is clear? Rate of heat flow from A to B like this. Now thermal resistance L by Ka. If we consider Wien's displacement law, lambda T equal to constant. The more you give the more temperature means wavelength is less. Relationship temperature of the system and wavelength radiated by the hot body. Again, from Newton's laws of cooling. Now we are considering Newton's laws of cooling. Newton's laws of cooling. Newton's laws of cooling. We are considering Newton's laws of cooling. Suppose surrounding temperature theta 0. Now theta 1 to theta 2 it takes T. So we have theta 1 minus theta 2 by T equal to K. Theta 1 theta 2 by 2 minus theta 0. This is very important formula. Thank you all. Next class we shall meet again.